Hello, and welcome to Chapter 5.2 from the Introduction to Statistics Think and Do book. In this chapter, we'll be talking about binomial probability distributions, and I'll give you the definition and the properties, but it's worth going back to 5.1 for just 1 second, where we did the very first example from 5.1. We create a little table, a probability distribution here for the number of heads in 3 tosses of a coin. Right? You can get 0, 1, 2, or 3. And then we gave the probabilities over here. This was considered a general discrete probability distribution, but it's also a very good example of a binomial probability distribution. So let's go back to 5.2. Keeping in mind that table about the number of heads in 3 tosses of a coin. And we'll go to full screen. Okay, so a binomial probability distribution is a type of discrete probability distribution that comes from a sequence of trials that satisfy these properties. 1, there are a fixed number of trials. For example, in that example, we were going to flip the coin 3 times. The results of the trials are independent, meaning the results from one trial does not affect the probability of the results from the next one or the one after that. They're independent. Each trial has all outcomes classified into 2 categories, usually success and failure. Now in the last one we had heads, so we could have heads or tails, and we'd call maybe heads the success and the tails the failure. But sometimes it doesn't necessarily mean there's only 2 things that can happen. It just means you have to categorize the 2 things into success and failure, which is, rolling a 6-sided die, you could call getting a 1 a success and not getting a 1 a failure. Okay, so, and the probability of success remains the same for all trials. What that means is that as time proceeds, the probability of getting that head does not change. Right? It stays at 0.5 the entire time. So we're going to have some notation that we're going to be using throughout this chapter and future chapters. And so we're going to actually come up with a formula for these things. So it's worth getting the notation out of the way now. So little p will denote the probability of a single success. And Q will remain 1 minus P for the rest of this book. Right? In other words, P plus Q will always equal 1. That's the probability of a single failure in this case, because P is the probability of a single success. N is the number of trials. They would flip the coin 3 times. X denotes the specific number of successes. That's the discrete probability distribution X, the same X. And this notation here, P of X given, there's that same given line. P of X given NP is said like this. Probability of X given N and P. So P is capital P is probability, and little p is the probability of a single success. So, sorry about the excessive use of the letter P, but in a course that has a lot of probabilities in it, you're going to get a lot of P's. So what this says, P of X successes, the probability of X successes in N trials with a single probability of success equal to small p, is what we're denoting. Okay, so before we start, and we're going to come up with a formula for this, right? But that's on the next page. We're going to go into these properties first. Suppose you're taking a 15-question multiple choice quiz, right? Each question has 5 options, A, B, C, D, and E. Now, you randomly guess at every question. You have a random guessing generator in your head. You can just randomly grab these things. Let X denote the number of correct guesses, right? And on a 15-question multiple choice quiz, you can get between 0 and 15 correct guesses, right? So verify that X, which is the number of correct guesses, follows a binomial probability distribution. right? And then I want you to determine N, P, and Q. First, are there a fixed number of trials? Yes. This quiz has 15 questions, and then I'm done. Are the results of the trials independent? Yes. Getting one answer correct does not change the probability of getting the next answer correct, right? Each of the trial has 2 categories of outcomes. Sure, there is correct or incorrect, or success and failure, right? And does the probability of success remain the same for all trials? Since there are, 5 options for all questions, yes, the probability is always 1 in 5. So the probability of a single success is 1/5, or 0.2. Q is 0.8. Remember, P plus Q always equals 1. And then N is the number of trials. And that equals, what are we doing this? We're answering 15 questions. Right? Okay, so we do that situation there does result in a binomial probability distribution. We're going to go back to the same convention for independent events, because if you remember, one of the properties is that the results of the trials are independent. But sometimes they're dependent, but the dependency is so small we neglect it. And so the convention for when to neglect the dependency is when the sampling size is less than 5% of the population, right? Less than 5%, just like from the last chapter in probability. So here's the idea. We have a huge can of, so here's a your turn problem, so we'll go on this in detail. We have a huge can of mixed nuts containing 60% cashews. It's a huge can. Thousands of nuts. And you randomly select 20 nuts. Let X denote the number of cashews you get, and verify that X follows a binomial probability distribution. So the first thing we have to check, are there a fixed number of trials? Yes. I'm going to grab 20 nuts. All right. Are the results independent? Well, not really, because if you select a nut and it's a cashew, that does sort of alter your probability of getting a cashew on the next draw. But since we're assuming this is a huge can of nuts, and we're only selecting 20, we'll assume that our small sample of 20 is less than 5% of our huge can. Right, however many that is. So we will go with convention here and say, all right, they are independent enough. All right. What about? See, the other one. There are only 2 outcomes. There's cashew, which we call a success, and not cashew, which we call a failure. And again, assuming the events are independent, right, our sample size, our 20, is less than 5% of the population, which is the number of nuts in the can, the probability of success remains the same at 20%, right? Sorry, 60%. Right, though it does change very slightly depending on what you get, the can of nuts is big enough that we're going to let that go and say not only are the trials independent, but that the probability of success remains the same for all trials. So this one you have to sort of stretch the rules a little bit using this convention. All right, so here's the formula. Don't be afraid. It's a pretty harsh formula, but down below we have a way to do this with a table, which is a lot easier. So here's how the formula goes. The probability of X successes given N trials with a single probability of success equal to P is this N, that exclamation point is a factorial. N factorial over N minus X factorial times X factorial. All times P to the X times Q to the N minus X. And again, Q is 1 minus P. Right? You may be wondering, what is this factorial sign? Basically what it means is if you start, say you have 6 factorial, what that is that's decreasing sequence of multiplication. So you get 6, 5, 4, 3, 2, 1 with multiplication in between each one, right? And 3 factorial is 3 times 2 times 1, and so on. And the only little catch to all this is that the 0 factorial is actually equal to 1. Right? So if one of these terms turns out to be 0, then you'll have a 0 factorial, in which case you replace it with a 1. And there's a reason for that, but there's no need to get into that. Okay, so we have our formula. We have what factorial means. Let's give it a shot. Suppose you're taking a 15 question multiple choice quiz. Each question has 5 options. That means your probability of a single success is 1/5, which is 0.2. And because you're randomly guessing on each question. You're not even going to read the question, you're just going to randomly guess. The first question is, what is the probability that you get exactly 2 questions correct? Well, we're going to use this formula right here, 5.3. And here again, the P, the probability of single success, is 0.2. Q is 1 minus P. And there's 15 trials. And we want the probability of getting exactly 2 correct. So the way this works, there's n factorial. There's n minus x factorial. There's x factorial. There's P to the x and Q to the n minus x, right? And so if we stretch all this out into a single fraction, that 15 factorial is all this, 15 times 14 times 13 times 10. And then below it, we have a 13 factorial right here, 13 factorial, and down here is 2 factorial. And we still have these parts that come along for the ride. And something wonderful happens here, and it happens pretty much every time you use this formula. We get a lot of cancellation. What I mean is that if you look at this 13 factorial down here, that cancels with this 13, 12, 11, 10, 9. These are all gone. So a lot of that cancels out. And in fact, you can take, so what we have is 15 times 14 over 2 times 1. Right, which is just, 15 times 7. So that whole messy fraction part will always result in a whole number. In this case, it's 105. And so after you get through all that, then you plug in the 0.2 to the 2, 0.8 to the 13, throw that in your calculator, you get 0.231. And remember, this is a probability, so it always has to be between 0 and 1. If you ever get a binomial probability that comes up less than 0 or bigger than 1, you did something wrong with the formula. So on the your turn problem, very similarly, now I'm asking, what is the probability that you get exactly 4 questions correct? So it's the probability that x equals 4, n is still 15. The probability of a single success is still 0.2. So there's the n factorial, n minus x factorial, and x factorial. 0.2 to the x, that's p to the x, q to the n minus x. And what you should notice is very similar to this one up here. You're going to get 15 times 14 times 13 times 12 times 11 times 10 times 9 times 8. But this 11 factorial will cancel with the 11 on down from the 15 factorial. So that all I have here is the 15 times 14 times 13 times 12. And then the rest will cancel with this 11 factorial. Over 4 factorial is 4 times 3 times 2 times 1. P to the x, q to the n minus x. Right. Now when you plug that all in, the fraction here again always ends up as a whole number. P to the x, q to the n minus x. And when you plug all this into your calculator, you get 0.188. right? So there's so that's fairly difficult, and it's not particularly fun, especially if all you're using is a scientific calculator. But one thing you should notice is that this thing out front with the factorials, that will always reduce to a whole number, and you'll usually get a lot of cancellation. So that sort of helps for doing that by hand. But there's an easy way, but we can't use it all the time, and it's using the tables on pages 337 to 339. And so here's the idea. If you want the probability of X successes in N trials, or the probability of a single success equals P, in other words, you want the probability of X given N comma P, we can use this table. And here's how you use this table. Let me go pop it up. Okay, so these are the binomial tables. And what you want to look for is N. N denotes the number of trials. P will denote the probability of a single success, so in our last example it was 0.2. And then X will be the number of successes. So if you only have 2 trials, you can only get 0, 1, or 2 successes. But if you have, say, suppose you have 10 trials, N is 10, we'll say for the sake of consistency, P is 0.2. Notice you can have anywhere from 0 to 10 successes. So the tables get bigger as we proceed. Alright, so let's go back to where we were. So let's answer these 2 questions, number 1 and number 2, using the table. Alright. What is the probability you get exactly 2 questions correct on our 15 question multiple choice quiz? Well, we have X is 2, N is 15, P is 0.2. So when you go to that table, we're looking for N is 15. Alright, so 15 trials. So that's this table here. P is 0.2, and I wanted to find the probability of getting exactly 2 successes. So at the intersection of this row and this column is 0.231. So that is a lot easier than the calculations we did above. Right, 0.231. Notice that's what we got up here. A lot of work. What about the your turn problem? What is the probability you get exactly 4 questions correct? Well, again, it's a one line. You just go here and you look quickly. P is still 0.2, N is 15. That's our number of trials. Only now I'm looking for 4 successes. So I go to that row, this column, 0.188. Much better, right? That's a lot faster. And that's the same answer we got by doing it by hand. What if I want to find the probability that you get 6 or more questions correct? So again, keep in mind we still have P equals 0.2, N equals 15. I'm going to find what's the probability that X is greater than or equal to 6. And to do that, again, I go back to the table. So no longer am I looking for exactly 4. I'm looking for 6 or more. Alright. So if I go over here, that's all of these numbers. So I'm going to add up all these numbers. And the question becomes, what do I do with this star? And the answer is up here. Star indicates a value less than 0.0005, but still positive. So the convention for us table users is to treat star equal to 0 when you're adding these things up. So we're going to add up all these probabilities. Because look, we can get 6 or 7 or 8 or 9, on and on, correct. So when you see the word or, you start adding. So we'll add all these up, 0.043, 0.014, 0.003, 0.001. And when you do that, you get 0.061. For the next one, your turn problem, what's the probability that you get less than 4? Well, again, we're going to go right back to that table. Less than 4. I'm going to erase all this. So I'm looking for 4, less than 4, so it's actually these ones here, which under this column, 0.2, are these four numbers, right? So you get 0 correct, 1 correct, 2 correct, or 3 correct. So we add up those, right, because we're using OR in there. So we add up those 4 numbers. And when we add up those 4 numbers, we get 0.64. So that's the probability that you'll get less than 4 correct if you guess on all the problems, which is pretty high. So they're a pretty good shot you're going to get less than 4 correct. Alright, so we're going to start using these probabilities to define when something unusual has happened. And we did this before when we discussed an unusual IQ or an unusual height, where we said it was more than 2 standard deviations above the mean. Well, here's a similar situation. We're going to start defining what it means to have an unusually high number of successes and an unusually low number of successes. And if we have X successes and N trials, that is unusually high. So it's high if the probability of getting X or more is small. How small? Less than 0.05. It's an unusually low number if the probability of getting X or fewer is small. Right? It's not just a matter of what the probability of getting exactly that many is. I mean, that can be small as well, but the probability of getting X or fewer being small will define what we call an unusually low number of successes. Okay, and I will do a couple examples right below here. Just a quick note. This is similar to the definition of unusual that we had from chapter 2.3, and is a preview of the difference between a 1 and 2-tailed p-value, basically. So they would actually be almost the same, except that the more than 2 standard deviations away that we discussed in chapter 2.3 is sort of a 2-tailed situation where you can be away in 2 different directions. Whereas here, we're talking about something being small on one side or the other. So let's take a look. Let's do an example. This is probably this is confusing. All right. And here's the idea. They look like the same definition, don't they? What makes them different is a number is unusually high if the probability of X or more is less than 0.05. It's unusually low if the probability of X or fewer is less than 0.05. So that's the only difference, but it's an important difference. Okay. We're going back to our multiple choice quiz. 15 questions, 5 options. So the probability of a single success is 1/5 or 0.2. You're going to randomly guess at every question. We're going to use the binomial probability table to answer the following questions. Would 6 correct answers be an unusually high number of correct guesses? So you have to go to our table, and we're looking at 6 or more. So we did this already. So if you add up all these, we're going to find out what the probability of getting 6 or more is. And when you add all those numbers up, you get 0.061. Now that is not small enough to be considered unusual. It is not less than or equal to 0.05. It's bigger. Right? So 6 would not be an unusually high number of correct guesses. I ask, would 7 correct answers be an unusually high number? Then we go to the table. And it looks similar to what we did, only now we no longer get 6. We get 7 or more. And when you add those 3 numbers up, on the stars, which we count as 0, you get 0.018. So the probability of getting 7 or more is very small. That makes 7 an unusually high number of correct guesses. Right. The example of an unusually low number of successes. Suppose I have my huge can of mixed nuts, 60% cashews. Randomly select 20. Would 6, right? So look, if it's 60% cashews and you select 20 nuts, you expect, say, about 12 cashews, right? 60% of 20. But you get 6. And so we're asking, if you got 6, would that be an unusually low number of cashews? So we go to our table. We look for, let's see, 20 trials. So we need 20 trials that we're grabbing 6 nuts from the can. Probability of success, probability of cashew is 0.6. And we want to know, is 6 or fewer? 6 an unusually low number. So to do that, we calculate the probability of getting 6 or fewer, which is just these numbers here, 0.005 plus 0.001. And the thing to notice about that is that it's 0.0006. And don't let the 6 and 5 thing confuse you. That is smaller than 0.05. And it has an extra 0. So 6 would certainly be an unusually low number of successes, right? And that's because the probability of getting 6 or fewer is small. How small? Smaller than 0.05. Would 9 cashews, so you're expecting 12, you get 9. Would 9 be considered unusually low? Well, let's go take a look. We go to our table. Right there. And we're looking for 9. So we actually get a few more than what we had before. So 9 or fewer. These right here. Right? And when you add all those numbers together, whoops, we get 0.0127. And that is not less than 0.05. So 9 is not unusually low. Right? So that's the trick. Remember, you're always comparing to 0.05 for as far as unusual goes. But when you're looking at unusually low, you use a less than or equal to sign. And when you're looking for unusually high, you use a greater than or equal to sign. Alright, and again, all software packages and graphing calculators have binomial probabilities built in. And they're usually pretty easy to use. So you can certainly go to stevenstats.com and check out how to do that and all sorts of things, SPSS, Minitab, TIs, things like that. Okay, so that pretty much wraps up this section. So I will see you in chapter 5.3, if I can close this down. Nope. Bye-bye.